Hello and welcome to Lecture 2 of the Energy Unit in Phys 1101. And in this one we're going to look at some simple cases where we can use conservation of energy, and then I'll just set up the case where things get not so simple, and we'll start looking at that in the next lecture. At the end of the last lecture we saw that this funny expression here, half mv squared plus mgy, turned out in free fall to be constant. And so we identified this constant as our total energy, and this piece here, the half mv squared, is our kinetic energy, the energy of motion, and this mgy is an energy of height, our gravitational potential energy. Let me just warn you that this is really only true in cases where gravity is the only force doing work. Now, for now, we know that's free fall. But as we'll see, there are other cases as well where this is true. In other words, other cases where gravity is the only force doing work. But until we have a better definition of work, we won't really be able to figure out when that's so. My other comment is that I very blithely multiplied through by m, saying that I was doing it because I felt like it. But of course that's not true. I was multiplying through by m because I knew the m had to be there. And just think about it. If you are using a hammer, a light hammer has less capacity to do work on a nail than a heavy hammer does, right? It won't drive the nail as far if it's going the same speed. So it's fairly clear that the energy should depend on the mass, and we will eventually see, using our definition of work, that it works like this. Let's carry out a unit analysis quickly. So look at the kinetic energy. The mass is in kilograms, the speed here is in meters per second, and so we get kilograms times meters per second all squared. And if you look at the gravitational potential energy, you have the mass in kilograms. G is an acceleration, so it's in meters per second squared. This y here is a distance, so it's in meters. And either way, you come up with the same units, right? You have to, because you have to be able to add these together, so they must have the same units. And it's kilogram meters squared per second squared. And we're going to define that as the joule, which is our unit of energy. Let's return to this case of me throwing a ball up into the air, but let's now do it with numbers and see how we can use this to solve for things. So let's say that when the ball leaves my hand, it's going up at 10 meters per second. And I've set my axes down on the floor, and let's say that at the moment it leaves my hand, it's a meter above the ground. And for whatever reason, we're interested in how fast this ball is going when it's 3 meters above the ground. So I'm going to start by drawing an energy bar chart. And so I'm talking about an initial time and a final time. So this is just 1 and 2. And we know that initially it's got a lot of kinetic energy, so I'll call that K1. And it's got not an awful lot of gravitational potential energy, so I'll call that UG1. And then later, at time 2, it's got less kinetic energy and more gravitational potential energy. And we know in free fall that the kinetic energy and the gravitational potential energy are constant, or they add up to a constant, the total energy. So K1 plus UG1 equals K2 plus UG2. And notice how I've lined that up. I'm really just taking my energy bar chart and I'm converting it into this formula. So the energy bar chart is just a visual way of getting your conservation of energy equation. Well, now we can just replace each of these with the formulas for the different types of energy. The kinetic energy is a half m, and I'll call that V1 squared, and the gravitational potential energy is mg, and I'll call this Y1. And the kinetic energy after, or later, is a half mv2 squared, and that plus the gravitational potential energy mgy2. And so now we want v2. We want to know how fast this is going at the end, so I'm just going to solve for that. So I've come up with 7.75 meters per second. Now, look at this. I could have done all of this using uniformly accelerated motion methods that we've known for weeks and weeks now. So you could be forgiven at this point for thinking that energy methods aren't very useful. But we will eventually see how they're useful in all sorts of cases where we can't use uniformly accelerated motion. Let's check your understanding of what I just did. So this is a situation almost exactly like the problem I just worked, except instead of the ball being thrown upward, this ball is being dropped from rest. So it's starting off at some height, and it's just been released, so it's stationary at the start, and at the final time it has gone some distance down. And this point, the system is the ball and the Earth, is sort of subtle, and we haven't talked about this yet. And so I'll just mention it now, and I'll talk about it more later. But it's important that the system here includes both the ball and the Earth. If it didn't, then the system wouldn't be able to have gravitational potential energy. I'll explain why that is later. For now, don't worry about it. So, which of these bar charts is the most correct energy bar chart?